Okay, so let me start directly with random variables. Okay, so what is a random variable? Okay, random variable is a function from sample space to real line. Okay, so if you can imagine that there is an experiment where you are tossing a fair coin two times, for example. If you're tossing a fair coin two times, what is your sample space? The sample space are all possible outcomes, list of all possible outcomes. And what are the possible outcomes when you toss a fair coin two times? There are four possibilities. You might observe head first, and then tail second, or maybe both heads, tails first and head second, or maybe both tails. So these are the four possibilities. Okay, so that's your sample space. Okay, now I can actually think of a random variable like maybe I'm interested in number of heads. So number of heads is a random variable. So this is just a verbal description of the random variable. So if you really think about it, number of heads is actually a function from sample space to real line, because if the outcome is two heads, then this number of heads will take value 2. If the outcome is just one heads, which happens in two possibilities, heads tails or tails heads, in that case number of heads will take value 1. And if there are two tails in this particular experiment as an outcome, then the number of heads will take value 0. Okay, so it's a function from sample space to real line. Okay, so that's a random variable. Is that clear?
Yes, Professor.
Okay. Okay, so there are two types of random. In fact, there are actually more than two types, but the most commonly used ones are there are two types of them. One is the discrete and the continuous. You can also have some kind of mixed random variables. Which have the point mass, as well as it's actually continuous over some range of values. So it's possible. We can also have mixed type of random variables, but we'll be mostly dealing with either discrete or continuous random variables. Okay, so what are the discrete random variables? So what is a discrete random variable? Well, discrete random variable is a random variable whose range is either a finite set or a countably infinite set. Okay, and the PMF is basically a function from range of the random variable to 0 1, and it is defined in this way. So probability that a random variable x takes value k is basically you just have to figure out the event that x equals to k, and just figure out the probability associated with it. Okay, and that's going to give you the PMF. Okay, just to give you an example. Okay, let's consider the same experiment that I just told you about. Suppose the experiment is tossing a fair coin two times. Okay, in that case the sample space is HH, HT, TH, and TT. Okay, and this random variable x is basically number of heads. Okay, so what is the probability mass function associated with this particular random variable? So px, well, of course, I mean, we have to figure out what are the possible values that x can take first. So that's going to give you the range of x. Okay, so what are the possible values that x can take when this is your experiment, tossing a fair coin two times? Well, it can take either value 0, 1, or 2, right? I mean, that's the range, right? So what is px0? Px0 is probability that x takes value 0. Okay, so this is the probability of this event x equal to 0. Okay, and when is it the case that x equals 0? Well, number of heads is 0 when you observe two tails, right? So this is probability of the event consisting of this outcome tt. Okay, and since all outcomes are equally likely, this is 1 by 4. Okay, similarly, you can figure out what is px1. Okay, px1 is probability that x takes value 1. Okay, which is equal to probability Now, when is it the case that number of heads is 1? Well, number of heads is 1 in these two cases, right? I mean, HT or TH, in both these cases, number of heads is 1. So we are going to get, 1 by 2, right? Okay, and what is px2? Well, px2 is probability that x takes value 2. Okay, and when is that going to happen? Well, this is an event which will occur when this outcome occurs, right? So which is HH. Okay, so we are going to get what? Probability of this event, which consists of this only one outcome, HH, and the probability of that is 1 by 4. And this is the PMF of random variable X. Have you understood this?
Yes, Professor.
Okay, so likewise you can have some other experiment corresponding to some other experiment. You can have you can have any type of random variable which is defined on that particular sample space, and for that particular random variable we can have a PMF associated with it. Okay, so that's what PMF is. Okay, then you also have an alternative way of representing the distribution of a random variable. You can actually use cumulative distribution function. Okay, so cumulative distribution function again is a function defined from real line to 0, 1, and it takes a value which is basically fx of x is probability that x takes value less than or equal to x. Okay, so now this is what you're going to do. Okay, probability that x takes value less than or equal to x. Is that fine? Okay, so of course because this event x less than or equal to x gets bigger and bigger as x goes up. So clearly the CDF is a non-decreasing function. Okay, and as x tends to negative infinity, this event shrinks to empty set. Okay, therefore the limit is going to be 0. Okay, and as x goes to infinity, this event expands to the entire sample space. Okay, so therefore the CDF goes to 1. Okay, and CDF is also right continuous. Okay, so let's quickly figure out the CDF of this particular random variable that we have just defined. Okay, so how do you figure out the CDF of this particular random variable? Well, fxx is equal to probability of the event that x is value less than or equal to x, and it is equal to what? Okay, it is well, for x less than 0. Okay, so what is the probability that x takes value less than or equal to x when x is less than 0? It is 0, right? Yes. Okay, and when x is between 0 and 1. Okay, so notice that when x is between 0 and 1, there is only one outcome that is there in this event. Okay, which is tt. Okay, so probability of that is 1 by 4. Okay, and when x is between 1 and 2, in that case, what is the probability that x will be less than or equal to x? Well, in that case, this particular event will consist of three outcomes, HT, TH, and TT. Okay, so the probability of this particular event containing these three outcomes will be 3 by 4. Okay, and what is uh, x? What does this event consist of? X less than or equal to x when x is greater than or equal to 2. Well, when x is greater than or equal to 2, it consists of the entire sample space, right? I mean, it's the entire sample space. This event is the entire sample space. So the CDF will take value 1. Okay, you can also, if you want, you can plot it and check that this is right continuous, or you can just look at it and check that it is right continuous. So of course it is a constant function, in the open interval 0, 1, in the open interval 1, 2, in the open interval 2 to infinity, in the open interval negative infinity to 0. So definitely it is continuous over these open intervals. But if I look at these endpoints 0, 1, and 2, at these points this particular function is right continuous but not left continuous. Okay, so we can definitely say that CDF is going to be right continuous, but left continuity is something which is not guaranteed. Is that clear to everyone?
That's clear.
Okay, okay. Okay, so the first very important random variable which is used a lot in applications is Bernoulli random variable. So we say that X is Bernoulli P random variable if it indicates whether an experiment or a trial that results in a success with probability P is a success or not. Okay, like for example, you can think of an experiment where you are rolling a fair dice. Okay, and let's say getting a multiple of 3 is considered a success. Okay, so if you roll a fair dice, okay, what is the probability of succeeding in this particular experiment? So if you define success as getting a multiple of 3, so what is it?
1/3.
1/3. Is that okay? Is this fine? Because you have 3, 6. These are the favorable outcomes, and you divide it by the total number of possibilities, which is 6. So you're going to get 2/6, which is 1/3. Okay, so it's a Bernoulli 1/3 random variable. Is that okay? Okay. So so this is how you can actually represent the Bernoulli PMF. Okay. In using the bar graph. Okay, so this is Bernoulli PMF for p equal to 0.3. So when p is 0.3, the probability of success or probability, so success is indicated by 1, okay, and failure is indicated by 0. Okay, so what is the probability that x takes value 1? It is basically p. What is the probability that x takes value 0? It is 1 minus p. Okay, so if p is 0.3, okay, then you can see that this is the height here is 0.3, and the height here is 0.7. Okay, and when p is 0.5, you can see that it's just 0.5, 0.5, for both 0 and 1. Okay, and when p is 0.7, then it is 0.3 for 0 and 0.7 for 1. Is that fine?
That's fine.
Okay, yeah, so we can also I mean we can do this like, and we can also write a code for it. I can just quickly tell you like how to yeah, generate this in Python. Okay, so okay, so can just x is equal to np dot array. Okay, 0, 1. Okay, and p the corresponding, or let's just probs. Okay, probs is np dot array. Okay, well, so let's say if p is 0.4, okay, then you can say 1 minus p comma p. Okay, now all that you have to do is just you have to use let me just run this once. Okay, now all that I have to do is this, that I just have to plot this bar graph. Okay, so this is how you can do it. So plt dot bar. Okay, and then you put X on the horizontal axis, and you put probs on the vertical axis. Okay, and then PLT dot show. Okay, this should work. Okay, so I guess it's just taking this as some numeric value. So what you can do is uh, let me see. Yeah, now this is fine, right? Okay, so I've just converted them into strings. Doesn't really matter. Okay, and now this is okay, right? Is that fine? So you might also want to label the graph. For is that okay? Fine. Okay. 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 So the next one is again very very interesting and very important. It's a binomial random variable. Okay. Uh, so what is a binomial random variable? So if you just imagine the same experiment that I was just telling you about, where you are rolling a fair dice. Okay. So just now just imagine that you roll this fair dice 5 times. Okay, and you are interested in basically number of times you get a multiple of 3. Okay, so what is the distribution of this particular random variable? Okay, so it turns out that this is binomial 5 comma 1 by 3. Is that okay? It's binomial 5 comma 1 by 3. Okay, so this is a PMF associated with the binomial NP random variable. Okay, N is basically number of times you are repeating the Bernoulli P trial. Okay, where P is the probability with which trial results in a success. Okay, so N is the number of trials. Okay, P is the probability of success in each trial. Obviously these two will together determine the number of successes. Okay, and since it's a random variable, we would like to figure out what are the probabilities associated with different number of successes. Okay, so this is basically your binomial PMF, the probability mass function associated with binomial NP random variable. Okay, so for n equal to 10 and p equal to zero point 0.3 and zero point 0.7, I've just plotted uh, the PMFs. Okay, so you can see that for p equal to zero point 0.3, okay, when p is smaller, so probability of success is smaller. In that case, the smaller number of successes have taller bars. Okay, and the larger number of successes have uh, smaller bars. Okay, for smaller p, and it is understandable, right? I mean, if success probability improves, then the more number of successes are more likely, with higher success probability. Okay, so if you see comparison between p equal to zero point 0.3 and p equal to zero point 0.7, this particular graph shows you that. Is that fine? Is that okay?
It's clear, Professor.
Okay. Of course, we can use the scipy library to access the PMF of, we have already seen that, we can use the scipy dot stats. Okay. So let's see. Yeah. from scipy.stats, we can import binom. I think that's the word for it, but we can always check. Okay. Okay. Let's. Take this off. Yeah, so it is binom. Okay. So we can just import binom. Okay, and then rest is just straightforward. So let's do some problems. Okay, let's also plot some PMF. Let's plot and let's do one problem related to binomial distribution. Okay, so okay, so let's say n is, okay, just a minute. Okay, so plot the PMF of X. Okay, so let's plot the PMF of random variable X, which is binomial 12 comma 1 by 4. Okay, so how do we do that? Well, so let's just quickly check. So so of course, the first thing that we have to do is we need to check what are the values that this particular random variable can take. So we know that this particular random variable can take values from 0 to 12, right? Okay, so it can take values 0 from 0 to 12. So if we print X, we'll get that. Okay, so it takes value from 0 to X. Okay, the next thing that we have to do is we have to figure out the PMF associated with each of these values. Okay, so let me put n equal to 12. Okay, and p equal to 1 by 4. Okay, and then probs is, okay, so what are the probabilities? Okay, so for finding the PMF we can just use this PMF. Okay, and so the first parameter is basically the probability that X takes value k. Okay, and this is n, this is p. Okay, so all that we have to do is basically binom dot PMF. Okay, so we have imported this, and this is a function within binom. So we are just going to put binom dot PMF, and then instead of k we'll put x, because these are the inputs, and n is 12, p is 1 by 4. So we just close the brackets over here. Okay, and then all that we have to do is just do the same plt dot bar. Okay, uh, x probs. Okay, and then plt dot show. Okay, and let's run this. Okay, so this is the PMF of binomial 12 comma 1 by 4 random variable. Is that clear?
Clear.
Okay. Now let's solve a problem. Okay, suppose, so related to binomial random variable. Okay, so suppose x is, or maybe suppose the experiment consists of tossing a fair coin 100 times. Okay, suppose the experiment consists of tossing a fair coin 100 times. Okay, and let x be the number of heads. Okay, so you have to figure out what is the probability of this event. So find the probability that x takes value between 48 and 52. Do it. Okay, do this. You have 2 minutes. Okay. Okay, are you done? Okay, so first of all, tell me what is the distribution of x?
Binomial 100 1 by 2.
Binomial 100 1 by 2. Perfect. Okay. So now we know everything. So all that we have to do is just use the appropriate function uh, from the scipy. Okay, and get this. Okay. So what are the x values? So this is one way to do it. Of course there are other ways as well. This is one way in which you can do it. You can just create an array. Okay, because you are interested in values from 48 to 52. You can just create an array from 48 to 53. Okay, because that will include 48, 49, 50, 51, 52. Okay, and then you can figure out the probs. Okay, so how do you do that? Well, exactly this. Binom dot pmf x and p. Okay, fine. Okay, and once we have this, then it's just about finding the sum, right? Okay, let's run this. Okay, so it's just close to 38%. Okay, is that fine? Okay, another way to do the same thing is you can actually use the CDF. Okay, so how to use CDF to do it? Well, you can just print binom.cdf. Okay, so 52 np, okay, minus, okay, okay, so since you want to include 48, so I'll just put 47 over here. Okay, and let's run this. Okay, and of course we'll get the same thing. Is that clear?
Yes, Professor.
Okay. Okay, so this is binomial. Okay, we can now move on to the next distribution. Geometric. Okay, so what is the geometric random variable? So actually there are two versions of geometric random variable that you'll find in textbooks. One version is what I have here in the slides. Another version is something that and it's also there in many other textbooks as well. Not just in these slides. The other version is basically there in the documentation for scipy. But they are actually kind of similar. Okay, so let me tell you exactly what geometric random variable is and what is the difference between the two versions. Okay, so we say that X is geometric P if it is the number of failures until the first success in successive Bernoulli P trials. Okay, so you can just imagine this experiment that I'm rolling the fair dice. Okay, and for me the success is getting a multiple of 3. Okay, and I keep rolling this dice, and keep observing the outcomes, till I get a multiple of 3. So basically, this is what the experiment is. Okay, so I keep, I roll this once. If I get a multiple of 3, I'll stop. If I don't, then I'll roll again, and I keep rolling till I get the multiple of 3. Okay, so one version is basically, counting the number of times you fail before you succeed. Okay, so this is what I have provided over here. Number of failures before the first success is your geometric random variable. Okay, so it is possible that you might fail 0 times, and which will happen if you get a multiple of 3 in your first trial itself. Okay, it is possible that you might fail once, twice, thrice. It's possible that you might fail a lot of times. I mean, it's any number of times is possible. Okay, and what is the probability associated with each of them? It is given by p into 1 minus p to the power x, and the logic is straightforward, because if you are interested in that number of times you fail is exactly x times. Okay, then 1 minus p will get multiplied x times, and then of course it has to be followed by a success, which means that you have to multiply it by p. So probability that you'll fail x number of times is p into 1 minus p to the power x. Is that clear? Okay, that's one version. Okay, another version actually don't count the number of failures but count the number of trials. Okay, number of trials until the first success. In that particular version, the random variable will take value 1, 2, 3, 4. It will never take value 0 because there'll be at least one trial. Okay, and it will always be one more than this. Okay, so it is just 1 plus this. So if for that particular version, the PMF will be uh, you know so what is the probability that the number of trials is x? It is p times 1 minus p to the power x minus 1, because if number of trials is x, then you must have failed exactly x minus 1 times. Okay, and then before getting the success. So it is p into 1 minus p to the power x minus 1. Okay, that's the only difference. Okay, otherwise they are exactly the same thing. Okay, fine. So both these random variables are, you like the term that is used to describe these two random variables is the same. It's a geometric random variable. Is that okay? So of course, if the probability of succeeding in each trial is going to be smaller, then it will take you longer to succeed. So you can actually see that number of failures are fewer when probability of success is higher. Okay, so like zero failure is very likely, when probability of succeeding in each trial is zero point 0.7. Okay, and it is of course relatively less likely, if probability of succeeding in each trial is smaller. Is that clear to everyone?
Yes.
Okay, so why don't you do one thing, quickly plot the PMF of geometric uh, 0.6. Okay, so do that, and share your code on the chat. Okay, so okay, so plot the PMF of X geometric 0.6 for values of X in the set 1 to 15. Okay, so I have told you to plot the PMF for X geometric 0.6 according to the interpretation in the scipy library. Okay, so in the scipy library, it's the number of trials. Okay, so you don't have to do any kind of changes or anything. Just do it in a routine way. Okay, otherwise, if you want to plot according to the interpretation given in the slides, you may have to do some adjustments, because probability that x takes value 1 will now be probability that x takes value 0 in case of, if you use the interpretation in the slides. Okay, so just go by the interpretation of the scipy.stats library and plot the PMF of geometric 0.6 random variable, okay, for values of x in the set 1 to 15. Let me just create a post on Piazza. You can post your code over there. Okay, Okay, so I've created this post. You can just post your code over here. Okay, and then I'll just you know run this over here just for your reference. This is a code that I've used to plot the PMF of binomial. Yeah, this should work. Okay, so let's just see. Okay. Okay. So first of all, we have to import geom. Okay. Uh, so let's quickly check that. Just a minute. Okay, so I think it is geom only. Okay, just a minute. Okay, so this is
It is
geometric.
geom, Professor. It is geom.
It is geom. Okay. So yeah. So yeah, that's it. So just do the same thing. From scipy.stats, you can import geom. Okay, and then then p is 0.6. Okay, so you can see over here, right? I mean, this is k minus 1. Okay, the reason is because, as I've just told you, because the interpretation here is number of trials until first success. Okay, so p is 0.6. Okay, and the x's that I'm interested in are from 1 to 15. So x is np dot arrange. Okay, so we'll start with 1. Okay, and then because we are interested in 1 to 15, so we'll just put a 16 over here. Okay, and then the next step is figuring out the probs, which is just use the geom.pmf. uh, this is geom.pmf. So of course you can see here over here that p is of course is going to take exactly the value that we have assigned to it, 0.6, and these are the points, right? So just yeah, absolutely, just geom.pmf xp, that's right. Okay, and then rest is just straightforward. Okay, it's the same thing, just plt dot bar x probs. Okay, and then plt dot show. Okay, so this is the PMF of geometric random variable. Okay, geometric 0.6 random variable. Okay, now of course the range of values that this particular random variable can take is from 1 to infinity, but we don't really have to bother plotting beyond in fact even 10, because the probability is so small that it's just it's almost negligible. Is that clear to everyone? Okay, so this is a good enough representation of the PMF. Okay, we can quickly also check what is the probability that that you will just need one trial. Okay, to succeed. It's just zero point 0.6, right? Because with 0.6 probability you will succeed in the first trial itself, and that is why, the height is 0.6 when X is 1. Okay, and for two trials, so it should be that, you fail the first time and then you succeed, so it's 0.6 into 0.4, which is 0.24. Okay, which explains this height. Is that clear to everyone?
Yes, Professor.
Okay. Okay, so another, very interesting and important random variable, which you'll see a lot in applications, not just in economics, but in other disciplines as well, is Poisson. Okay, so what is Poisson random variable? Again, it is also something which measures, or basically which is used to model situations where there is uncertainty about how many times a particular event will occur. Okay, so like, like for example, you can have a situation where you are interested in, uh, number of customers who will arrive at your store in next 1 hour. Okay, or number of or basically number of emails that will arrive in your mailbox in next 1 day. Okay, so something like that, I mean, so in order to model such scenarios, we use Poisson distribution. We say that X is Poisson lambda, if its PMF is given by this. Okay, probability mass function is given by this. Okay, where lambda is a rate parameter. Okay, so what is this rate parameter? So basically it tells you the average number of successes, or basically average number of times the event will occur. Okay, so we can imagine, let's say if there are roughly around 5 emails per day in your email box, then if you are interested in the number of emails that will arrive in the next 24 hours, or basically next day in your mailbox, then you can say that you can model it as a Poisson 5 random variable. Okay, so lambda is 5, so you can think of it as a rate parameter. So from the historical data, you have the average, which is 5 emails per day, and you are interested in basically what is the distribution of number of emails that you will receive in next 24 hours. Then the way to model that is, you can actually use Poisson 5 random variable to model this kind of setup. Is this clear to everyone?
Yes, Professor.
Okay, so again, of course, if lambda is higher, then you can expect higher number of successes. Okay, so lambda is, you can, as I've told you, it's a rate, rate of success. So higher the rate of success, higher will be the number of successes. As you can see, for lambda equal to 1, the bars are taller, for smaller values of X, and as lambda goes up, the bars, for smaller values of X gets smaller, and for uh, relatively larger values gets bigger. Is that clear to everyone? Okay. Okay, so it turns out that there is a very interesting connection between Poisson and binomial also, because binomial also measure number of successes. Poisson in some sense also measure number of successes. So what is the connection? So when n gets bigger, and p gets smaller. Okay, so if number of trials, just keep increasing the number of trials, keep reducing the probability of success of each trial, then it turns out that binomial converges to Poisson, which is a very interesting result. Okay, so let me tell you, this is the result, okay, that I'm talking about. So as n goes to infinity, as probability of success shrinks to 0, okay, and we make sure that n times Pn is always lambda. So just fix the product n times Pn, so that when n goes to infinity, Pn goes to 0, the product stays at lambda. Okay, so in such a scenario, what happens is that that the PMF of binomial NPN converges to PMF of Poisson lambda. Okay, which is a very very interesting result. Okay, we can also just quickly check that, using using Python. Okay, so what we can do is basically we can just imagine an experiment where probability of success is very very small. Okay, and the number of trials is large. Okay, and we can actually compare the PMF of Poisson with PMF of binomial. Okay, some values of Poisson with some values of binomial, and we can see that there'll be not much difference. So basically, the idea is that, when n is high and p is small, then you can approximate binomial probabilities by Poisson probabilities. So if you are interested in the binomial probabilities, you can just use the Poisson probabilities instead to approximate the binomial probabilities. Okay, is that fine? Okay, so let's quickly check that. Okay, let's just what is it? Okay, so what we'll do is, we can consider some binomial random variable with n high and p small. Okay, so okay, suppose x is binomial 100 comma 0.01. Okay, so what we have to do is find the exact probability that x takes value less than or equal to 0, x takes value less than or equal to 1, x takes value less than or equal to 2, and so on and so forth. Okay, and we have to also find the similar probabilities for using the Poisson approximation. Okay, and we'll just compare them. Okay. Okay, so okay, so let's do this. Okay, so let's do this. So you have uh, 5 minutes. Why don't you just do this quickly? Okay, I'll also post a question on. Okay, so just write the code and you can actually share it over here, and I'll just run this. Yeah, that's right. Okay, that's right. Absolutely. Okay, so because lambda is 1, so you can directly put that. Okay, and you will get it. Okay, and yeah, that's exactly what you have to do. Absolutely. Very good, Sudarshan. Okay, so now you can just print. Okay, and then you can also print. Okay, let's run this. Okay, you can see that they are like very close to each other. Okay, I mean the values are kind of quite close. Is that clear?
Yes, Professor.
Okay. Okay, so let's now another very important random variable is the indicator random variable that you can come across in problems. Okay, so indicator random variable is just it's just like Bernoulli. Okay, I mean it's just that it's defined on an event. Okay, so indicator random variable indicates whether a particular event has occurred or not, by taking value 1. If the event occurs, then it takes value 1. If the event doesn't occur, it takes value 0. Okay, so if you really think about it, it is a Bernoulli random variable with parameter equal to probability of a. Okay, so that's all that it is. Okay, I mean it's not I mean it's the same thing as Bernoulli p. Okay, where p is probability of a. Okay. Okay, so what is the expected value? Expected value of a random variable is just you just do the summation xpxx, you'll get the expected value of x. So we can of course use Python to figure out the expected value of any random variable. I mean, it's just summing xpx, right? I mean, that's a very standard kind of calculation. So you just have to take a vector x, you have a vector px, just take the dot product, okay, and then use the sum function. Okay, so once you want to take the uh, yeah, so you just take the dot product and you'll get it. Okay, is that fine? Okay,
That's fine, Professor.
okay. So then this is another one, negative binomial random variable. This is another discrete random variable. But here, what happens is, it's just, you can just imagine it's a generalization of geometric random variable. Okay, so in geometric random variable, we are interested in number of failures until first success. In geometric random variable, we are interested in number of failures until rth success. So here r is also another parameter. Okay, so suppose you are interested in number of failures until fourth success. So you keep tossing a fair coin until you get heads 4 times. Okay, I'm not saying 4 times in a row. Okay, I'm just saying until you observe heads 4 times, in the entire sequence. So what is the distribution of that? It's actually negative binomial. Okay, again, you will find how to implement negative binomial in Python. You can actually have a look at the documentation. You'll get it. Okay, so and then you have hypergeometric. So basically, you should know how to solve problems related to these kind of situation. So I can give you a situation where you might have to use in the homework. Also, I can give you a situation where you have to identify which random variable I'm talking about in that particular problem, and then you might have to actually use the corresponding scipy library, basically functions to actually figure out the numbers, and then post it as your solution in the homework. Okay, so I'm just going over it so that you know like under what condition you can use this, under what condition you can use that, and so on and so forth. Okay. Okay, so another one is hypergeometric. So hypergeometric is also very, very important random variable which you see a lot. Like for example, if I randomly pick 5 cards from a well shuffled deck of 52 cards. Okay, so basically it's like I'm serving you a poker hand. Okay, so what is the probability of getting one ace, okay, or two aces, or three aces, or four aces? So basically, these number of aces that you will get in this 5 card hand will take value from 0 to 4. Okay, what are the probabilities associated with them? So it turns out this particular random variable, which is equal to the number of aces that you will get if you are served 5 cards from the well shuffled deck of 52 cards, we call this a hypergeometric random variable. Is that clear? Okay, another example is, you can just imagine this white ball example. So suppose you know suppose there are total number of n balls in an urn. Okay, and out of those n balls, m are white. Okay, and you randomly choose n balls from that urn. Okay, then what is the probability associated with getting x number of white balls? Okay, so it turns out that it is going to be m choose x, because I mean, you are from those m white balls, you will be choosing x of them, so m choose x, and from the remaining non-white balls you'll be choosing n minus x of them because the total sample size is n. So that's going to be the numerator, and the denominator is going to be n choose n. Okay, and these are the PMFs associated with hypergeometric. Again, you can find the documentation, as well as the implementation of hypergeometric in Python. It should be available on scipy. Okay, is this fine?
Yes, Professor.
Okay. Okay, so now let's talk about some continuous distributions. Okay, and how to visualize them. Okay, one very important continuous random variable that you'll see a lot is uniform random variable. Okay, and it has again lots and lots of applications. Okay, in fact, in simulations, if you have to draw a random number from some distribution that you are interested in, it's possible that the scipy library or some other library may not contain an implementation of that, but uniform drawing a number from uniform distribution is always part of every stats library. Okay, and if you know how to draw a number from uniform distribution, there is a theorem that tells you that you can actually draw numbers from any distribution if you know how to draw a number from a uniform distribution. Okay, so that theorem is known as universality of uniform. Okay, which is very very useful, I mean, in that sense, because if you can draw a number from uniform, you can draw a number from any distribution. Okay, using a trick. Okay, which we'll see. Okay, so anyways, so this is a uniform random variable. So we say x is uniform AB if the density is 1 upon b minus a when x is between a and b and 0 otherwise. Okay, so what that means is, so if we imagine x is uniform 2 to 4, okay, then x can take values between 2 and 4. Okay, so that's a range of values that x can take. Okay, so the density will be basically just 1 upon 2, and so what is this density going to do? So basically, we call this random variable a continuous random variable because there is no PMF associated with it. There is a density function associated with it, and if you are interested in finding the probability that x takes value between a and b, then you just need to integrate the density function from a to b. Okay, and that's going to give you the probability that x takes value between a and b. Is that clear to anyone?
Clear.
Okay, so for a continuous random variable, if you are interested in what is the probability that x takes value equal to some number, so if I'll ask you what is the probability that x takes value equal to 3 when x is uniform 2 to 4, what is your answer?
Could you come again, Professor?
So the question is, suppose x is uniform 2 to 4, what is the probability that x takes value equal to 3?
0.
0. Is that okay? Is this clear to everyone? It's a continuous random variable. So obviously, one way to see that is, if you just put 3 over here and 3 over here, a is 3 as well as b is 3, you'll get a 0, right? Okay, so of course, probability that x takes value equal to a certain number is always 0 for a continuous random variable. Okay, but probability that x takes value in a certain interval, that may not be 0. Okay, and it turns out that probability that x takes value between negative infinity and infinity, that will be 1. Okay, so you can easily see over here that probability that x takes value between 2 and 4 will be 1, because if you integrate 0.5 from 2 to 4, you will get 1. Okay, can you check this quickly? Integrate 0.5 from 2 to 4. okay, and check that you'll get 1. Okay, you can also because integral, definite integral is also, the area, you can also see that, this is 0.5 and this length is 2, so 2 into 0.5 is 1, and of course, that's why you're getting 1. Is that clear to everyone?
Got it, Professor.
Okay, so now let's look at, scipy for uniform. So now we are going to go back to the continuous distributions. Okay, so okay, so this is uniform distribution. Okay, and if you want to implement uniform, then you have to import uniform, okay, from scipy.stats. Okay, so let's do that. Okay, so let's plot the PMF. Okay, sorry, PDF. It doesn't have a PMF, it has a PDF. Okay, so let's look at, you know uh, okay, so the input to the PDF is X values, and this location and the scale. So we'll see. Okay, we'll see, don't worry about it. Okay, let's plot the PDF. Okay, okay, now what I'm going to do is I'm going to take some X values. Okay, np dot arrange. Let's say I want to plot uniform 2 to 5 random variable. Okay, so it's uniform from 2 to 5. Okay, so I'll start from 2. Okay, end at 5. Okay, and increment will be from by 0.01. Okay, is this fine? Or maybe just 1 to 6. Okay, but I'm interested in plotting uniform 2 to 5 random variable. Okay, let me just write that on the top. Plot the PDF of okay, so what I'll do is I'll collect probes. Okay, probes will be uniform.pdf. Let me put a 6 over here. Okay, so 2 to 5 is within 1 to 6. Okay, fine. Uniform.pdf x. So location is 2. Okay, because it starts from 2. Okay, and the scale is 2 plus 3. Okay, so 2 plus 3 is 5. Okay, I think this should work. Otherwise, we'll just do the adjustment. I think this should work. Okay, now what I'm going to do is plt dot plot. Okay, x props. Okay, and plt dot show. Okay, so let's run this. Okay, and that's exactly what we were interested in. Is that okay? This is a PMF. Sorry, PDF. Okay, of binom of uniform 2 to 5 random variable. Is that okay?
Yes, Professor.
Okay. Of course, you have other functionalities. You can figure out the CDF. You can figure out the percentile, whatever you wish, so let me ask you a question then. Okay, so suppose X is uniform 100 to 200. Okay, so suppose X is uniform 100 to 200. Okay, find the following. Okay, the probability that X takes value less than or equal to 125. Okay, also find the probability that X takes value greater than 190. Okay, also find X such that probability that X takes value less than or equal to X is 1 by 4. Okay, do this. Expected value of X.
Professor, are we supposed to send you the code, or can we just?
Yeah, just send me the code. You use the code to do it. Okay, I mean, of course, you can also do it without using the code, but see which function you can use to figure out these quantities. Just send me the code. Okay, let me also post this on Piazza. And what is the expected value of X, without using the code? What is the expected value of X?
A plus b by 2, which is 150.
Yeah, which is 150. Absolutely. Okay. Okay, so let's see. Okay. let me just copy this. Okay, so okay, I just have to check the documentation. So but location and scale are fine, no problem at all. This is also fine. 1/4 CDF, absolutely, this is also fine. I think SF should be 1 minus the CDF. If that's the case, then this is also fine. Okay, let's
That's
just
right.
is it that? Yeah, so yeah, so it's 1 minus the CDF. Okay, great. So I guess this is precisely what you have to do. Okay, is that fine? Okay, very good, very good. Okay, is this clear to everyone? Any questions, anyone?
Yes, Professor.
Okay, okay. Okay, so let's move on to the next one. Okay, now this is extremely important. Normal distribution. Okay, so okay, we say that X is normally distributed with mean, mu, variance, sigma square. Okay, if it has this density function. Okay, and so basically mu is, you can think of as a location parameter. Okay, and sigma is the scale parameter. Okay, sigma is also the standard deviation. Okay, and mu is the expected value of the random variable. Okay, so if you see over here, these are the density plots of these three different normal random variables. Okay, so the green one is the one which has the highest standard deviation. As you can see, the spread is highest in case of the green one. The standard deviation is 2 in this case. Okay, the blue one is the standard normal. Okay, with mu 0 and sigma equal to 1. And the red one is actually the one where standard deviation is 0.7. Okay, and all of them have the same mean. Okay, and these are the corresponding CDFs, cumulative distribution function plots. Is that fine?
Yes, Professor.
Okay, so do you want to do an exercise on plotting the normal PDF, or we can skip that if you wish? I mean, it's just this. Do you want an exercise? Or let's do it. Okay, so let's do an exercise, and we'll do some problems. Okay, related to normal distribution. Okay, so okay, so suppose X is normal 2 comma, so mu is 2. Okay, and sigma, which is a standard deviation, is 4. Okay, so plot the density of X. Okay, from, let's say, -5 to 10. Okay, well, maybe 2 to Yeah, -5 to 10. Okay. Okay, just do this first exercise. I'll give you more. Okay. So suppose X is normal with mean 2 and standard deviation 4. Plot the density of X over -5 to 10. Okay, over this interval -5 to 10. So even though it takes value from negative infinity to infinity, but you know the chances of it taking values outside this interval is very, very small, so we can ignore it. Okay, so you just have to draw the density over the interval -5 to 10. Okay, you can use a similar kind of uh, code to do it. Okay. That's right. Okay, so let's just quickly do this. Okay, so X is, you can just take again X's from -6 to 10, and this is so let me just use the same name that I'm using. Okay, probs. Okay, and then that's right. Okay, and then plt dot show. Okay. Okay, so this is going to give you the PDF plot. So let's run this, and this is how it looks. Well, it turns out that this only contains 95% of the observations. So if you want, to get so you can just expand the interval. I mean, this is, you can actually figure out that it will contain 95% of the observation by using the CDF function. Okay, so norm.cdf. Okay, so you can evaluate the norm.cdf at 10. Okay, location parameter is 2. Okay, and the scale parameter is 4. Okay, and then you subtract from this. Okay, norm.cdf -6. Okay, and then you just print it out. Okay, and you will get that this is close to 95%. Okay, the reason why it is close to 95% is because of that 68%, 95%, 99.7% rule, that that roughly 95% of the observations will be within 2 standard deviation away from the mean. Okay, so if you see 2 standard deviation away means 2 into 4 is 8, so 2 minus 8 is minus 6, okay, and 2 plus 8 is 10. Okay, so within 2 standard deviations away, this is the percentage of observations. Okay, so if you want uh, a bigger picture, you can actually uh, just make the interval bigger. Okay, that's all that you need to do. Is that clear?
Yes, Professor.
Okay, similarly, you can also have another random variable, which is the exponential random variable. Okay, which is also very useful. Like, for example, uh, if you are interested in basically modeling a scenario where you are interested in how much time you'll have to wait for the next email to arrive in your mailbox. If the rate at which the email arrive at your mailbox is 5 emails per day. Okay, so lambda is exactly the same rate that we were talking about in the Poisson distribution. Okay, so lambda is like the rate at which the success occurs. Okay, and if you remember, Poisson actually tells you number of successes in an interval of time when the rate of success is given by lambda. Now, exponential random variable, how is that connected? So basically, you can imagine that you are modeling you are interested in basically how much time you'll have to wait for the next email to arrive in your mailbox. So starting from now, okay, if the rate at which the emails arrive at your email in your email box is five emails per day. Okay, so lambda is 5. The amount of time that you'll have to wait when this is the rate of arrival for the first arrival to occur is modeled using exponential 5 random variable. Is that clear to everyone?
That is clear, Professor.
Okay, so it turns out this exponential and Poisson has this very interesting connection, and this whole process, this arrival process that I've just described is also known as Poisson process. Okay, so where arrival occurs in this fashion. Okay, so this is again a very interesting property associated with exponential random variable. We can again do similar kind of exercises related to it, but I'll just post them on Piazza. You can try them. Okay, I'll some post questions related to it. Okay, but before stopping for today, let's do this one very interesting uh, you know uh, theorem, which is universality of uniform. Okay, which I was talking about, that if you know how to draw numbers from uniform distribution, then you can actually use it to draw numbers from any distribution. Okay, so that's actually very interesting thing about uniform. Okay, so, and it follows from this particular result. Okay, so suppose you want to draw numbers from this distribution fx. So you know the CDF, but you don't know how to draw numbers from this distribution, but you know how to draw numbers from uniform distribution. So how can we use our capability to draw numbers from uniform distribution to draw numbers from the distribution of our choice? Is that clear? Have you understood the question?
Yes,
Could
Professor.
you come again, Professor?
Yeah, so what I'm saying is, so of course I know how to draw numbers from uniform distribution, right? I mean, so we can just quickly see that. Okay, from the uniform distribution, we can use RVS, right? We can use RVS to draw numbers from uniform 0, 1 distribution. Do you agree? Yes. all that we have to do is we just have to specify the size. Okay, so let's say if we draw 100 numbers from uniform distribution. Okay, and if we just plot the histogram, okay, how is that going to look? Okay, it will be more or less like this. Okay, I mean, of course, if you want for law of large numbers to work, if you just pick a larger sample, then it's going to be more or less at the same height. Okay, so you can see that this is actually telling you that you are actually generating numbers from the uniform 0-1 distribution. So we know how to draw numbers from uniform 0-1 distribution in this way, right, using RVS function. Is that clear?
Got it,
Yes.
Professor.
Okay, now if so we know how to generate numbers from uniform distribution, but it's not necessary that we have to always generate numbers from uniform distribution in simulation, right? I mean, it's possible that we might have to generate numbers from some other distribution of our choice. Like for example, you may want to generate numbers from some other CDF. Okay, let me give you one example. Let's say suppose the CDF is x squared from 0 to 1. Okay, CDF is x squared from 0 to 1. Okay, I mean, it's a perfectly valid CDF, right? I mean, it's increasing. So x squared is an increasing function from 0 to 1, and beyond 1 it takes value 1, below 0 it takes value 0. Okay, so basically, suppose let me just write the question. Suppose I want to generate numbers, generate random values, okay, of x, where x is distributed, okay, according to the distribution f, okay, and f is given by the following. So f of x is equal to x squared, okay, okay, so suppose I want to generate random numbers from this distribution where the CDF is given by fx equal to x squared, where x takes value between 0 and 1. Sorry about that, it's not 0 otherwise. It's 0 if x is less than or equal to 0, and 1 otherwise. Okay, is that fine? Okay, so it's a valid CDF, right? I mean, it's non-decreasing, and it is in fact continuous. Okay, it's not only right continuous, but it's also continuous. Okay, and all the limiting conditions are also met. Limit as x tends to negative infinity, it goes to 0. Limit as x tends to infinity, it goes to 1. So it's a valid CDF. So I want to generate random numbers from this distribution, okay, whose CDF is this. So how can I accomplish that? Okay, that's what we are interested in. Okay, so So this theorem actually tells you, if you know how to generate random numbers from uniform distribution, you can actually use this functionality to generate random numbers from any distribution. Okay, so let me first quickly prove this theorem. It's just a two-line proof. Okay, and then we'll generate random numbers from the distribution that we have just provided, fx equal to x squared. Okay, so now what does this result says? This result says that if x is distributed according to f, okay, then if you put, if you consider this transformation f of x, okay, where x is distributed according to f and f is the CDF. So if you just use CDF function to transform x, then it turns out that the distribution of f of x is uniform 0, 1. Okay, so let's first prove this, and then we'll see how we can use it, okay, to generate random numbers from this distribution. Okay, so let's prove this, that this has a uniform 0, 1 distribution. Okay, so how should we show this? Well, so let's call this y. Okay, so what I'm going to do is I'll figure out what is fyy. Okay, so fyy, of course, because this is a CDF function, so it will only take values between 0 and 1. So the range of y is between 0 and 1. Okay, that's for sure. Okay, so fyy is less, okay, which is equal to the probability that fxx is less than or equal to y. Okay, so let's assume that it's a continuous distribution. So within the range, this will be a strictly increasing function. So if it is a strictly increasing function, then we can write it like this: fx inverse y, right? Okay, and what is this? This is just a number, right? So what is the probability that x takes value less than or equal to fx inverse y? It is fx of fx inverse y, okay, which is nothing but y, right? Okay, so the value of the CDF at y is y. Okay, what that means is that the density is 1 for y between 0 and 1, and it is 0 otherwise. Okay, because this is something that, of course, I used the fact that y is in the range of y, so that means y is between 0 and 1. Okay, so for y between 0 and 1, this is a CDF and this is a PDF. And if this is a PDF, then that means that y is a uniform 0, 1 random variable. Is that clear to everyone?
That's clear, Professor.
Okay, now how can I use this? Well, yeah, how can I use this to actually generate random numbers from the distribution that I'm interested in? Well, if fxx is uniform 0, 1, fx inverse y has a distribution fx, right? Because if fxx is uniform 0, 1, x is fx inverse y, and we know that x has distribution fx, so fx inverse y will have distribution fx, right? Yes, where y is uniform 0, 1. Is that clear?
Yes, Professor.
Yes or no? Now, if I know fx is x squared, so what is the fx inverse function? Square root of x, right? Square root of y, right? Yes or no?
Yes, Professor.
Okay, so now we are now we know actually how to do this. Basically, all that we have to do is basically, if I want to generate random numbers from this distribution, I can just generate random numbers from uniform distribution and take their square root. okay, and that square root will be actually a random number generated from this distribution. Okay, so how can we do this? Well, y equals, okay, let me do one thing. Let me call this u. Okay, okay, so I've already generated random numbers from uniform distribution. Now all that I'm going to do is this, that I'm going to take square root of u and call that x. Okay, and it turns out that these x's are from this distribution. Okay, and how can we check that? We can actually plot the histogram of x and see how it is like how it looks. Okay, so let's quickly do this. Okay, plt.hist x plt.show. Okay, by the way, if this is the CDF, what is the PDF of x? What is the PDF of x when x is between 0 and 1? Take the derivative, right? It's 2x. So it's like a triangle, right? It's a triangle, 2x. Okay, so this should also look like a triangle, right? The histogram. Thing just made some mistake. Sorry, y. This is u. Okay, sorry about that. Yeah. Okay, and it indeed looks like a triangle, right? Is this clear?
Clear, Professor.
Okay, so this is actually very useful. I mean, if you know how to generate random numbers from uniform distribution, we can actually use it to generate random numbers from any distribution. Okay, so I'll post some exercises. We can do one or two more examples in the next class, and then we'll move on to law of large numbers and central limit theorem. Okay.